So I want to think in this video about the fields that surround charged objects. So we've already talked about in a previous video the idea that charge is a property of all matter. So if I have a positive charge, it will have a radial electric field that surrounds it. And by convention, we show the field leaving the positive charge, going away from the positive charge. The reason we define it in this way is when we think about an electric field, we imagine what would happen to a positive charge if we placed it in the field. So if I was to put a positive charge here somewhere in the field, the force would act outwards because two positives will repel each other. So that's why the arrows go away from the positive. So this is our picture of an electric field around a single charged object. Now, if I do this with a negative charge, the field will look identical. It will be radial around a spherical object at least. But this time, imagine if I had the same positive charge in my near my negative charge, it would attract. So when we have draw a field, electric field, we have the lines going towards the negative charge. Okay, so this is our sort of field surrounding two charged objects. So this could be a proton, for example, and this could be an electron. Now what we're also interested in is what the field looks like when these charges approach each other. And now this is very similar to the way that magnetic fields interact. So if I have a positive charge and I have a negative charge like this, the field leaves the positive and will go into the negative. So the field, because remember it's radial, the shortest distance between 2 points is a straight line, so we will get a straight line between them. But then remember the field will be coming out in all directions around the charge, so it will then, at the other points, it will curve. Sorry, I've drawn the arrows the wrong way. Let me just correct that. That's the way the arrows should be. So remember, they go from positive to negative, not the way I just did it. But they will also be coming out of the object at other points. So I will have much larger. The one up here now will form a much larger field line into negative, and then some of the points there that would have been out here will still be out there. And obviously you can imagine this loop going in a huge circle. Again, always coming out of positive and into negative. So this is what the electric field would look like between a positive and a negative object. And obviously we know that the effect of this is attraction. Opposites attract. So there will be a force between these two charged particles, drawing them together. Now this is really important because this is an idea of forces acting at a distance. So imagine if I had just my electron sitting there on its own with no other charged particles near it. Well, in that case, the electron will have an electric field, but it's not going to interact. It's not going to do anything because it has to have another field for it to interact with. So when another field comes into contact with it, so if I now bring my positive and negative together and then the fields overlap, when they overlap, you then get this effect, and it's the overlapping of the fields which produces a force due to the electric field. Now we can also have the opposite of this, and the only thing that's different about a positive, this being between two positives and two negatives, is the way in which you draw your direction of your arrows. So if I have two positives, the key is that these two objects now are going to repel each other. So these field lines which show can never cross, and so they will literally bend away from each other. And and will never ever meet. And so there's this point in the centre where the field lines never cross, and therefore the electric field at that point is 0. So if you imagine that I was to place a negative charge perfectly between the two of these charges, if they were the same, it wouldn't go one way or the other, because each charged object would pull it by the same amount. Just like if I got a block of wood and I was pulling it with 2 elastic bands on each side. If I pulled it, if the forces were balanced, it wouldn't accelerate in either direction. It's only when I release one that it would then accelerate. So the field lines never ever cross, and then you basically complete the rest of the field quite simply. The same way that you completed, sorry, these lines should be straighter than what I've just done. Like exactly, was pretty much the same as we did when we had a single charge. So where the fields are no longer interacting, they would still be straight lines. And it's only where they approach each other where they deflect and the fields push away from each other. Just complete this. So that's what the field would look like if it was 2 positive charges. It would look identical if it was 2 negative charges that were obviously creating a repulsive force and were repelling each other. The only difference would be the arrows would all be pointing inwards, just because they always go in towards a negative charge. Just one final little situation to think about. One of the ways that electric fields were first investigated was between 2 charged plates. So if I've got 2 charged plates, so if I've got a and I give one of these plates a large charge. So if I make one positive because it has a deficiency of electrons, and I make the other negative, so I'm going to give it an excess of electrons, then I will get an electric field between these 2 charged plates. So the way that I would do this as well, just to make this into a circuit for a second, is that I would have to have a power supply that would provide a potential difference between these 2 plates. So I need a very high potential difference, or in simple terms, voltage between these 2 plates. So it's important. We'll come back to potential difference in a later lesson, but potential difference for the time being is a type of voltage. So I need a really big voltage in order to create a strong electric field between these 2 plates. So then to fill in my electric field, it always leaves positives and goes to negatives. Between the plates, it would be perfectly uniform straight lines, like so. And then at the very edge of the plates, it does curve ever so slightly. And this can be seen in various experiments where you take 2 charge points that act like plates, and then you use small particles like iron filings or pepper grains suspended in solution, and they line up with the magnetic field, and you can see these field lines, not obviously directly, but through the effect that they have on small uncharged particles. The only shape of electric fields that we haven't really thought about, which is an important one to just bear in mind, is what happens when you have a point. So if you have a pointed object, like a spike, spikes or pointed objects are more likely to discharge than spherical objects. And this can be seen in the Van de Graaff demonstration. So the reason for this is that if I just assume that this is going to be positive, then at the tip, you'll find that the field lines are closer together. and the closer they are, the stronger the electric field. And so you're more likely to get a discharge at this point because you will get a greater build-up of electrons right at the tip than you will halfway down. And so there's an extra thing to think about for all of these. Where the electric field is close, the lines are closest, then that is where the electric field is strongest. So in this example, this is radial because they're the same distance all the way around, and that's uniform, so it doesn't matter. The electric field is effectively the same strength everywhere. But obviously you can also see that the lines get further apart the further away you get, so the field gets weaker the further you travel away from the charge. Obviously, same thing here, that the electric field is much stronger closer to a charged object because the lines are much closer than they are at some separation. And this is again represented when we have a spiked or pointed object with an electric field around it. The electric field will be denser or closer together at the tip.